recording has started.
Potatoes.
So, that's pretty cool. Einstein's out, so it's his time to shine. It started today, so you know. All right. Actually, he was out earlier because of physical science. We're talking about him too. So, you know. All right. On Friday, we began talking about orbits, and we talked about the idea that once Newton realizes what gravity does or how it works, he starts putting some numbers together and starts looking at some things, and he knows that an object is going to fall 5 meters under the influence of gravity in the first second that it's under the influence of gravity, and that if, in theory, knowing how much the Earth curves, how much gravity pulls it down, he can calculate horizontally how fast that object would have to go in order for it to fall exactly the same distance that the Earth curves, and then it doesn't get any closer to the surface. And if that happens, we get ourselves a nice little circular path like this blue line right here, okay, where an object would just continuously being affected by gravity but never getting any closer to the surface. And we went through this calculation real quick, right, just like we did calculations in the last unit, and we found out that this equation would tell us how fast something would have to go to perform a completely circular orbit. Okay? If it's going slower than this speed, what's going to happen to it? It's going to eventually crash into the Earth. Okay? It might not be immediate, like throwing this ball across the room, right? But eventually it will crash to the Earth. That's pretty much how things that we have in space, quote unquote, land. We just slow them down a little bit, and eventually they hit the ground. Okay? Usually smooth landing, but sometimes not. So, but if it's going faster than this speed, we talked about the idea that it'll still go in an orbit, but it will go in an elliptical orbit. And we talked about that as it goes in this elliptical orbit, it doesn't travel the same speed, right? It slows down on the way out and speeds up on the way back in, and slows down and speeds up. Some practical applications of this, which we didn't talk about on Friday because we didn't get there. Have we ever heard of the concept of using gravity to slingshot us into a faster speed or something like that? Okay. You ever see Apollo 13? You saw Apollo 13. They kind of use that in Apollo 13, right? So talk about the idea. Here's my representation of Apollo 13. There it is. So it's like a command module thing, right? And then here's some windows, so you can see. But now I gotta. So it was pretty scary. Apollo 13. If I did this, maybe. No, it'd be more like that. So.
No, don't go near that.
All right, so if we get Apollo 13 in an orbit around the moon, as it gets closer and closer and closer to the moon, what do we know starts happening to it? It does get closer, yes. Yes. Let's not use it accelerates. It speeds up, right? So faster, 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 faster until you get to this point. Then what do? Well, if you let it go, slower, 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 right? But if you want to go someplace else, like back to the Earth, right? At this point, it's going as fast as it's ever going to be. So what do you do at that point? If you want to use Earth's, or if you want to go faster, right? Now's the time to hit the gas. Okay? Anybody ever hear of Voyager 1 or Voyager 2?
Yeah. Aren't those the rovers?
No, those are. That's Curiosity.
Called Voyager?
No. Voyager 1 and Voyager 2 are satellites that we launched back in the 70s. And we did this with them around Jupiter. Why Jupiter? It's huge. It's got a lot of gravity. So we put them in this nice little orbit, and Jupiter pulls them in faster, 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 faster. Then at this point here, boom, we hit the gas. Okay? Because Voyager 1 and Voyager 2 are still going. They have gotten themselves effectively out of the solar system, and are just Well, it's not a lot for it to hit out there, you know? Like, basically, the closest star to us is about 4.5 light years away. So, once it gets past, like, our solar system, not a whole lot there. Now, there is stuff in our solar system outside of Pluto, even though Pluto kind of got demoted. It's still, you know, it's still like in the club. He's just not like a full member, you know? It's like on probationary status, kind of, you know? But there's other stuff out there that's still considered our solar system. But once it gets past that, there's really nothing there. So it's just going to let it go. And it'll keep going because of the whole inertia thing, you know? So, but to get it out of the solar system, we had to get it going really, really fast for a reason why we'll talk about a little bit later on today. Evan, go ahead.
Like, what's the point of doing that? Like, doesn't it need to communicate with Earth?
Yeah, it still can communicate with Earth.
Does it take like a long time?
It takes a longer, but yeah, but it, you know, it still communicates with Earth. You know.
Eventually, when it was not be able to.
No, because that's actually a good point too. It sends out a signal, right? But that signal is a energy signal. It's a radio wave, basically. So it will just go. You know, I mean, it takes a while for it to get, you know, back and forth, but it'll still travel. It'll travel infinitely until it runs into something.
So we can communicate with things that are outside of our solar system, but we can't communicate with things on the like opposite side of Mars.
Well, we can.
Didn't they like? Don't the rovers only like?
Well, see, the thing too with things on the opposite side of Mars, just like the opposite side of the moon, if you're going to get a signal there, you have to have something to like bounce it. You know what I'm saying? Because if I'm here and I'm trying to see you, I can't see you, right? Because there's stuff in the way. But I would have to have something to bounce it. But if we're just going, you know, if we just want to communicate like out, that's fine. As long as there's nothing in the way between us and the satellite, we can talk back and forth all day.
Like the 8 other planets.
Talk. So now, the 8 other planets take up a real small percentage of the space between us and the edge of the solar system.
Yeah, but also Voyager's not that big.
That's true, but the rest of the planets aren't that big in, you know, relation to that either. So, yeah, it's pretty easy. It's pretty open lane of communication. So, yes, Ken?
What are they trying to find?
Nothing really. They're basically at this point. Those satellites originally were sent to Jupiter and sent to Saturn, I think, to learn about Jupiter and learn about Saturn. So they hung out in this elliptical orbit and kind of, you know, took some pictures and took some readings. And then after a while, when we got all the information we needed about those planets, we said, hey, let's just send it and see what happens. So, and actually, Kim, it actually has a bunch of information on it with the intention or with the hope that someday it would be found by some intelligent being that would be able to decipher it. So I mean, it's got like a map of our galaxy and where we are in the galaxy, and it's got a bunch of it's a record because back at the time that was the preferred mode of sound recording. But it's got like something like over 1,000 sounds from Earth. You know, like everything from like waves crashing to people singing to hearts beating and stuff like that. Just sounds that are representative of our planet. But it also has like a copy of like, it has like a picture of DNA and like what we look like and stuff like that, so that people that find it might be able to interpret that. So
Find out is it going to kill us?
basically, you know. So,
It's kind of neat.
hopefully not, but maybe, you know. So
What doesn't like want to get far enough from the sun also that it won't be able to do anything. You know, it's gotta get energy from somewhere.
it's true. So, but at this point, it doesn't use a whole lot of energy. It doesn't need any energy for propulsion because
Right, but
inertia just,
communicate
you know,
probably
lets it
takes a
go. So what?
To communicate, I'm guessing that probably takes a lot.
That's true. It's probably actually it's not really that much energy for communication, really. So I think I mean at this point, anything that they get back from it is sort of gravy. Like it did its job, and now it's just sort of like see what happens, you know. So yeah, I believe its official mission has ended, but I think it's still sending back information. Like what it's sending back, I don't really know. But yeah, I think its mission is officially completed. It's just sort of like let's see what happens, you know. So, but the idea being that, you know, he And that's important because of this concept here that we refer to as escape speed. All right. Our discussion of escape speed starts with this picture, which I realize is not the first picture on your set of notes, but this is an old picture, one that we've seen before, and it talks about energy. And we know that if we take some object and throw it up in the air, right, from an energy standpoint, as it goes up, kinetic energy decreases, potential energy increases. When it hits the top, all of the mechanical energy is in the form of potential, and then no kinetic, so it stops, and then it starts coming back down. And that's because gravity is acting on it the whole time, blah, 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 blah. So if we take a look at this lady in the, jumping onto the building, if we calculate that this object, in this case a lady, has 10,000 joules of potential energy up at the top of this building, if we want to throw it, if we want to throw something up to the top of that building, that's the size of that lady, how much kinetic energy would we have to give it at the bottom? 10,000. Right? On the way up, the 10,000 joules of kinetic are turned into potential. When it reaches the top, all potential, no kinetic, that object stops.
So we have 2 people.
Say again?
So we have 2 people fall.
Unless it's, some other inanimate object that's the same mass as that lady. Okay. Let's say, though, instead of giving it 10,000 joules of energy at the bottom, we gave it 10,001 joules of energy down at the bottom. Would it stop at the top of the building? No. When it gets to the point where it has 10,000 joules of potential energy, it still has some kinetic energy left, so it would go a little bit higher. Okay. That concept holds for any source of gravity. But because of the idea that as we get farther and farther and farther away from something, the amount of force of gravity decreases, the whole inverse square relationship, there comes a point when effectively the force of gravity between 2 objects is pretty much non-existent anymore. Okay? Now, mathematically that doesn't quite jive, but in reality that is the case, that we get to the point where there really isn't any gravity anymore between this object and that object. Okay? If we could calculate how much potential energy that object would have at the point where the force of gravity effectively goes to 0, let's say it's a bazillion joules. So at the point when the gravity of, let's say, the sun ends, this object would have a bazillion joules of potential energy. If we were standing on the surface of the sun and we threw this, I realize there's logistical problems with that, but if we threw it so that it has a bazillion and 1 joules of kinetic energy, when it gets to the top, what is it still doing? It's still moving. So what's it going to do?
Keep moving.
It's moving, but the sun's gravity isn't really pulling on it anymore. So what does it do? It just keeps going. So, right, what comes up must come down, right? Maybe not. Not if we throw it fast enough. Okay? How fast do we have to throw it? Well, that depends on a couple of things. This formula here is the formula for escape speed. Escape speed depends on a couple of things. One, it depends on how big of an object are we trying to get away from, this capital M. Like for our solar system, that capital M is going to be the sun. Okay? D is how far away you are from that object when you are quote-unquote throwing it. Okay? So if we're talking about the Voyager spacecraft escaping the solar system, we plug M into this equation, the mass of the sun. We plug D, the distance to Jupiter, because that's where we're trying to throw it from, quote unquote, right? And we can figure out how fast we would have to, quote unquote, throw that object in order to eventually get it out of the gravitational field of the sun. Okay? Does that make sense? We could do it for Earth, too, right? How fast would we have to throw this object to get it away from Earth's gravity? We can plug any numbers that we want in here. Now, this holds true for any source of gravity. If we start looking hard enough, we start finding weird things, like these. Okay? Black hole. Right? Notice, right? All kinds of stuff goes in there, right? Shopping carts, cars, a TV, some guy reading his newspaper, right? Okay? All of it ends up going in there. So what a black hole is you take this formula and you plug in the numbers for the star that we're, or the black hole itself. You plug in how far away you are from the black hole, and you get a number out of here. But that number is greater than 3.00 times 10 to the 8th power. Anybody know what that number is? It's the speed of light. There is enough mass, and you are close enough to this object, that the escape speed is greater than the speed of light, which is kind of a problem if you're trying to escape, because to our knowledge at this point in time, nothing goes faster than the speed of light. So I could be standing on the surface of a black hole, logistical problems notwithstanding, right? Okay. And I take this baseball and I throw it at the speed of light. Guess what? Still not fast enough for it to go out of the black hole. It would go up, it would stop, it would come back down. Might take a while, but it would happen.
That sucks.
Yeah, kind of sucks if you're there.
Yeah.
Obviously, I figured out the logistics because I got to the surface of the black
Right,
hole,
yeah.
so no problem. But
So we know you can escape.
that's true. So where do black holes come from? Black holes are formed when massive stars collapse into their middles at the end of their life cycle. It's obviously more complex than that, but it's the end of a star. Okay? And generally, that star was huge to begin with, and then it exploded at the end of its life. And what happens is the core at the middle, because of the explosion, gets crunched down so much that there's so much mass compacted into such a small space that the gravity around it is high enough that its escape speed is greater than the speed of light. Okay. The gravitational field is so strong that you can't really get away from it. Okay? And you end up with this. Okay? So a couple questions arise out of this. Okay? First, well, there's actually more questions than I thought of now. Okay? First, do we see black holes?
No.
No, right? Nothing goes out of them. Everything goes into them, but nothing comes out of them. So what do we see? We see a big black spot in the sky, and there's a bunch of stuff heading towards it. We're like, must be a lot of gravity there. Okay? That's our superhuman deductive powers
So
right
they
there.
just kind of like made up, like when they show you black holes, they just kind of made that up.
What, this picture?
Yeah, or like when they show you black holes, they just kind of make that up.
No,
Yeah.
you can see this stuff going.
I mean, yeah, it's kind of like a drain, but you can't really see the drain. You just see everything like going towards the drain. All of a sudden, it just disappears. Okay. Does that make sense or no?
Yeah, it does.
Okay. So, second, are there black holes just gobbling up everything around it? No. Okay. Here. Okay. No. Look, multiple exclamation points. Okay. Because, remember, your black hole used to be a star. Okay. That picture on the left is your black hole as it used to be as a star. I'll make that picture a little bigger. Actually, here, let me do this. Can't do that. I can do this. Okay? So here on the left is your black hole before it was a black hole. It was a star. And there was some planet. Planet Green. Okay? Planet Green used to orbit around this star that has now become a black hole. Now that this star has become a black hole, is Planet Green in trouble?
No.
No.
Depends.
Okay.
So it's not in.
It used to just orbit around this thing, right, as a planet. We've just taken the mass of this thing and crunched it down a little bit farther. Is there any more mass to this star now that it's a black hole?
No.
No, actually it's actually a little bit less than it used to be as a star. Okay. Are we any closer or farther to that black hole than we were when Planet Green was just a planet of that star?
Yes. farther. The radius.
But remember that D in that formula
Oh, it's from the
is from the center, right? So this is exactly the same distance as it used to be from the star. It's exactly the same mass. Would planet green know anything happened?
Yes.
Other than there used to be a big star in its sky and now it's not there anymore. Okay? But what would it do? Just keeps going, right? If our sun becomes a black hole,
We're good.
we're good. Well, other than the fact we lose our source of energy, but you know, but we don't. We'll stay in orbit though. We'll stay in orbit
That's
though.
all that matters.
That's, I mean, well, not really. So that's not all that matters. Ask Mercury. Mercury stays in orbit all the time, but things there don't go so hot. Well, actually, they do go hot. So, didn't really try to do that on purpose, honestly. So, all right, but that doesn't happen to us. All right, well, so things that turn into black holes don't just start gobbling up things around it. Now, let's say planet green sends out its own version of Apollo 13, right? They're less sophisticated. They don't have the windows.
It's bigger than the planet.
Yeah, it's bigger than the planet, not to scale. So they've used all the resources on planet green to build it. So, but once it gets here, now it's got a problem. Anywhere that used to be part of the star, but now it isn't because the star is smaller now, that's where we have a problem. Okay? So if things fly by, you get caught in the gravity, blah, 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 blah. Okay? So, do black holes gobble up everything around them? No. The gravitational field is only increased in areas that used to be taken up by the star itself. Okay? Next question. What happens when something goes into a black hole?
We don't know.
I don't really know.
Gone forever.
Yeah? So,
It
what?
just get compacted and added to that.
Well, we don't know what happens when it actually goes into the black hole. There is a spot around the black hole called the event horizon. The event horizon is basically the edge of the black hole. That's where you get to the point where light can't get out of it, and you don't see anything past that point. Now, what happens up until that point? Well, just like anything that happens under the influence of gravity. If I take this ball, right, and I, once again, logistically, standing on the black hole, right, and I drop this ball, what's going to happen to it?
Disappear forever.
Well, eventually, yes, but first, what's going to start happening to it? What happens to anything under the influence of gravity? What happens to this ball under this gravity?
Speeds up.
It falls, right? And as it falls, it speeds up. And that's what happens to the black hole, too. Okay? But as you get closer and closer and closer to the black hole, now things start getting interesting. Because as this ball falls towards Earth, technically, do all parts of the ball feel the same amount of gravity? The bottom of the ball is closer to the center of the Earth than the top of the ball. So the bottom of the ball actually feels more gravity than the top of the ball. Is that really a problem here on Earth? The difference is so small, you can't perceive it. But if you start getting closer and closer and closer to a black hole, now the amount of gravity that the bottom of the ball feels is much stronger than the force of gravity that the top of the ball feels. So what's going to start happening to the ball? The bottom of the ball is going to accelerate more than the top of the ball is going to accelerate, and now it starts stretching out. Okay? Until it eventually does what? Breaks in half. Okay? Then, those two pieces, okay, same thing starts happening. Out of that half, the bottom half, more gravity than the top half, stretches it out, breaks it in half. We refer to that, and I'm not even joking, I'm not making this up. It's referred to as spaghettification. Okay? I'm not making that up, right? That's actually real. It's actually a real term. Okay? And as things start approaching black holes, we start seeing evidence of this happening. And it would happen to you too. That your feet would start, depending on how you were going in, maybe you dove into the black hole. I don't know. Okay?
That's kind of awesome.
So,
Good way to die.
just get yourself a little platform out of your Apollo 13 and just, you know,
How would
All right. So we got that. Now, if you've been paying attention over the past 3-4 days, this whole idea of a black hole should raise some issues with you. Anybody got an issue with this idea of a black hole? How about if I take us back to this?
It has no
What has distance? What's getting sucked into a black hole?
masses.
But is it only masses though?
No.
It's also what? It's also, well, air is mass, but it's also light.
Which is mass.
What's the problem? Mass is energy. Does it have, or sorry, light is energy. Does it have mass?
Yes. Yeah.
No.
Equals MC squared.
That doesn't mean light has mass.
Well, if it's energy, you know, mass is energy.
No. It's two different forms of something. It's not mass, it's energy. And if it's energy, it doesn't have mass. So does gravity work on light? Not the way Newton thought it did, but guess what? It does. Okay? So, once again,
They just make shit up.
well, I mean, in essence, that's how science works. People make shit up, and then you test it, and then you're like,
I'm glad
easy, everybody, easy. As if you guys have never said that before, right? So, okay. But I was paraphrasing, right? So, yeah, people make stuff up, and then you test it, and it either tests out good or it doesn't. And when Newton makes up this idea of gravity back in the middle 1600s, everything's great. It all works until we start finding weird stuff like black holes. And we're like, it doesn't quite check out. Something must not be right. So, don't worry though, because we have a solution. Right? Whenever we have a problem in science, where do we go for answers? Right here. There it is. So, whenever we have a problem in science, we go to Einstein. Because Einstein figures it out. And you know what's even more frustrating for most people, like contemporaries of Einstein, although I don't think too many people harbored any, like, you know, ill will towards him. Einstein basically figures stuff out just by thinking about it. Like, he just sits around, he's like, okay, writes some things down, and he's like, okay, here, check this out. And never does like any experiments of his own, just thought experiments, so he calls it. He's basically just sitting around thinking about crap. He calls it a thought experiment, you know. But he's like, write some stuff down here. Check this out. Guess what? He's always right, right? Not always, but most of the time. So he starts thinking about this, and he goes, apparently gravity is not working like this. So there's got to be something else. So he goes, what if gravity really isn't gravity the way we think about it? What if gravity looks like this? Alright? So what if the universe really isn't space? What if it's this big, like, trampoline? Why trampoline? Because when we set things down in it, what happens to the trampoline when you put something on the trampoline? Trampoline bends, makes a little dip. So what Einstein says, not in so many words, but he says, hey, what if the universe is like a big trampoline? And things don't move because of gravity. Things are just rolling along the surface of the trampoline. And when they get a dip, or when they hit a dip in the trampoline, what are they going to do? They fall into the dip. Right? What would happen when those two things, when this metal object falls into the dip? Eventually, what's it going to run into?
Other objects.
did you drop the ball?
It's just rolling down the dip.
Oh, okay.
Right? Just rolled down the dip and ran into the thing that's at the bottom of the dip, that being the Earth in this case. Okay? So, mass, what Einstein says is that mass causes a fundamental change in the area around it. And that fundamental change is what we perceive as gravity. Now, the mass causes the change in gravity, or the change in the surface, but not the objects that move along it. Light is just like this metal marble. Guess what light does when it hits the dip?
Goes in.
Falls into the dip, just like anything else. So now, have we solved the problem of a black hole?
No.
Yeah. Here's a black hole. All right, well, no. So, here's the fabric of the universe. There's the sun. Or let's say the Earth. Okay? Oh. There's a black hole.
Just like Dig Dug.
Kind of like Dig Dug, if you want to think of it that way, right? So if we have an object that's rolling along the surface, if it hits the surface just right, boom, it goes down here like that. Okay, it falls into the Earth. Okay? In theory, could we throw this thing fast enough that it gets out of the hole and ends up back on the flat side?
Yes.
Guess what we just call that? Escape speed. Alright? Escape speed is how fast we would have to throw this thing to roll it out of the hole and get it up to here. Okay? But, if you got a bigger mass, you got a bigger hole. Alright? Black holes down here. I throw this thing with the speed of light, guess what?
It's not enough.
Doesn't get to the top. Falls back down.
Oof, thanks.
Good question.
He thinks of this! And his hair falls off. And it's even creepier. So, yeah, exactly. That's why he's a freaking Einstein. Because you're like, why couldn't it just be all like, hey, a black hole is weird, you know, and just leave it at that? Like, no, he has to come up with something to explain it, you know? And guess what? We do tests, and guess what we find out? Damn, he's right. That light actually does curve when it goes around stuff, when it goes around big masses like the sun. Guess when we'll find out about that?
Next week.
Tomorrow. Yes, sir.
So how come your fabric of the universe is all
Say again? It's a two-dimensional representation of a four-dimensional object. Yeah, I know. Totally sucks. But guess what? Right. We'll talk about that tomorrow, actually, too. So, yes, hold on. Wait. We still have like 5 minutes left till the end of the period. Here's a convenient breaking point. Emily, go ahead.
So can first, can nothing be above the line?
The line is the absence of any mass in the universe. So this would be like the space between stars or whatever. Okay? So Emily, like when something like, let's say the Voyager spacecraft is in between this groove that the sun makes in the universe and the groove that the next star makes in the universe, all it does is just rolls along the line. Okay? And because it's flat, it doesn't speed up or slow down, just like inertia says, right? So all of Newton's laws are taken care of with this. So nothing that Newton said was wrong, it just wasn't all inclusive to everything that's out there. So yeah, when you're in between things, that's like when you're in between mass in the universe. And so if if there's no gravity, it's just, you just roll along.
And can you see through a black hole if it's not black? Is it like invisible?
Yeah, it's like, so Emily, it's like looking into a well, but not being able to see. Like you can see the outside of a well, but you can't really see the bottom of the well.
What if you were to the left, right? You're looking, not looking down,
Here?
looking like across.
If you're like over here, see now, okay. This is kind of weird because now you're not in the universe anymore. like this is the universe up here, and this is some outside the universe place. So you can't be there, or at least we don't think you can be there. Okay? So yeah, you'd have to be up here. Oop. You'd have to be up here. So you may be considering to hang yourself because how you don't understand this, but it's okay, really, don't worry about it. Alright? Please don't. Alright? But yeah, so you have to be up here, and so yeah, it's like looking at a well. Like you can see the outside edge of the well, but once stuff goes in, you don't know what happens to it.
Across it?
Yeah, you can kind of see like maybe to the other side. Like you can see like what's on the other side, but you can't really see into it.
We should just watch Event Horizon.
You think? So,
It makes you weird.
yeah, I think totally. So. Yes, Evan.
Okay, so if like stuff is flying past this black hole,
Yep.
it's getting sucked in.
Yep.
Isn't the mass of the black hole growing so like the radius, like the gravity, like the expanding?
Technically, yeah.
So eventually the planet may get sucked in.
Maybe. So it's, I mean, we've kind of established that pretty much every single one of our galaxies has a black hole in the middle of it. So, you know, our Earth, or our sun is rotating around the center of the galaxy, but the center of the galaxy isn't like a really big sun, it's a black hole.
Kind of makes sense.
Kind of, right. So, what?
That make everything spin.
Yeah, it's gotta make everything spin. That's what it does. So, but yeah, we'll pick up tomorrow, talk about Einstein's theory of special relativity. It's gonna be great.